Okay, thank you. This is joint work with my student Yonjian Hu, Oriana Riva, and Shumana from Microsoft Research. So let me give you a brief introduction to what app links are. Suppose you are looking for a restaurant in a browser app, right? So I'm looking for a certain sushi place there. Then when you click on the link that's supposed to take you to the Yelp app, what actually happens, the way this is put in place, is the browser app sends a deep link or an app link to the Yelp app, and when you open the Yelp app, you land directly on a page that gives you details about that restaurant. And notice how you bypass the homepage, the Yelp homepage, which is in the middle there. So these are called mobile app links, are URIs that point to specific pages in an app, and they help you land on a specific page, as I did in Yelp there. Or for instance, if you want to play a certain track on Spotify, you can use a link like that and tell the Spotify app, okay, I don't want to land on your homepage, I want to land directly on that track ID and play that track ID supposedly. The same thing for, let's say, IMDb, right, when you want to see details about the movie. And this is also the mechanism that's used by intelligent assistants to tell you which movies are playing, for instance. Or if you want to request an Uber to this location, the mechanism is the same. The problem is it's really hard to discover such links at scale. And the other problem is coverage. App coverage is really low. Few apps expose few links, and this is what we try to address in this paper. So let me give you a flavor of how you can try to discover links. It's really cumbersome. So number one, you can look at the app's manifest, and this is the actual manifest of the Yelp app. So you have to scroll through pages and pages of supposedly links, but in the end, you're not going to get what you want. So on page 7, essentially, you're just left with the URL. So you know that if you want to launch the Yelp app on a specific page, this is the URL you should use, but it doesn't tell you about the parameter. Right? The parameters marked in red are find descriptor and find location are missing. So you have to find that somehow, and that's really, really hard if you don't have, if you don't know how to analyze bytecode. Another approach is to look at the counterpart. Look at the app's website, if the app has a website. Not many apps have websites. So for instance, this is the Yelp website, and if you look at the source, you see that actually there's a link there that gives you the parameters. But the problem with this approach is, right, so you have the parameters, you can guess the link, so to speak. The problem is not many websites that have, so websites that are app counterparts expose these links. So we did a study on top 14 most popular apps that have a website counterpart, and the result is even though the apps can have up to 10 or 20 links, only one or two are exposed in practice, so coverage is really, really low. On average, 1.5 links are exposed, but 9.6 links exist. So we have an approach called Elix that addresses this problem, addresses the discovery issue. So we use static analysis to discover more links in the app. And we're going to use a series of techniques to also improve coverage. So we discover more links, including non-exposed links that the developers and also the users should know about. The key insight is, as those of you who are familiar with Android know, Android apps are highly structured. You navigate from one activity to the next, and this is orchestrated by the framework. And the way to move from one activity to the next is via something called intent, that are the parameters needed to launch an activity. So our idea is we capture this intent statically and we observe how their parameters flow in the app, and we use that to reconstruct the link parameters. So I'm going to present some code from a sample restaurant app, and we're going to see how we can model this link extraction as a static taint analysis problem. So the idea is we're going to look at how parameters are propagating through the app and activity code, and the flow of these parameters actually defines the link. So this sample restaurant app takes an intent. So to land here, you're going to come by an intent, and the intent has the parameters that tell you what you're actually looking for, and the intent also contains some information that's going to be displayed on a screen that's stored in a bundle. So this sample app has two links. One, let's assume that you want to view details for a certain restaurant. So that's going to land you in a page where you can see, actually here, you can see the page title is set to the restaurant name, and the Google Maps location is set to the restaurant location. For instance, you want to just drive there. So that's one link. The second link, if you want to see, let's say, what other nearby restaurants are there, that's completed via another deep link that has a constraint called search. So the action, I'm going to come in here when the action is equal to search, and for that, I'm going to see a list of nearby restaurants. So this is the second app link. The problem is, if you want to discover this using just vanilla static analysis, what happens with static analysis when we get to a point where the two branches of an if-then-else merge, the information is merged, so you lose precision, and it's going to be impossible to discover the link because the two branches are conflated. So to address this, we use something called symbolic execution. There on the right, you see something called path condition. In symbolic execution, this tracks the predicates that have to hold in order for you to navigate down that path. So essentially, let me start with a simple path condition. I'm just going to denote that pi. The path condition to land onto the then branch here is going to be pi and I equals view, or intent equals view, and intent is not equal to search. Okay? And vice versa, the path condition for the other branch is pi and I equals search, and I is not equal to view. Okay? So with symbolic execution, we're going to fork the execution into two mutually exclusive symbolic paths that are represented by, characterized by those path conditions. Right? So this is great. It improves precision, but it's unscalable. As you can imagine, if I keep forking the execution every time I reach a new branch, we can quickly get into this path explosion problem. So to contain the path explosion problem, we use something called Path-Selective Taint tracking. So if you're familiar with taint tracking analysis, taint tracking tracks the flow of information from a sink to a source. The sink there is actually the intent in yellow. The source is whenever an intent is used to influence control flow, i.e. as a branch condition. So we use this taint analysis. What I did, I just inserted a little bit of code that saved instant state to give you an idea as to when taint analysis makes how taint analysis can make a difference. So we use this taint tracking, and all the branches that are tainted are marked in red. So you see that the bottom branch is actually tainted, is marked in red because it uses information from the intent. The top branch is not tainted, marked in green. So if taint tracking does not reveal that a certain branch or a certain branch is influenced by the intent, then we can safely merge those two paths, and that avoids this explosion problem. So coming back to the path condition, going into the program, or going into the activity, the path condition is pi. You see how the path condition is forked here, right? So we have two mutually exclusive paths, but I can merge them because the branch is not tainted, and this helps us, essentially this helps us contain the path explosion problem. Here, of course, the execution proceeds on two different paths. And we use some other optimizations like path killing and so on and so forth, and I defer to the paper for that. Okay, so the result, we're going to be able to extract app links. Remember, I said the flow of intent data is going to define the app link, so the specification is implicit, and we need this static analysis to make it explicit. So this is the link that's going to be extracted from the if branch. There on the bottom, you see the link as Elix-extracted, right? So we have the path constraint, and then we know that the link has three parameters: a string, a serializable, and a parcelable. We do something else called complex object reduction. Sometimes we see objects that have thousands of fields, and that's not really practical. So we do a second round of taint tracking and propagation to make sure that when we extract parameters, we only extract those parameters that are going to be used. And again, I defer to the paper for that. And of course, the second link, it's going to again have three parameters according to how the data from the intent is used. The paper also has other examples of extracted app links. These are some samples of, for instance, for open table. This is what the Elix-extracted app link looks like, right, for viewing restaurant information on a map. For Airbnb, if you want to search for room listings, that's the activity, and that's the string that lands you essentially onto that activity and with the correct parameters. For IMDb, if you want to see, remember that example from the beginning, if you want to see showtimes for a certain movie on a certain day, there are two parameters, the date and the ID for the movie. Right? So these are all automatically extracted and simplified by Elix. So moving on to the implementation and evaluation, this is our evaluation test bed. We have the static app link extractor, and then what we do, we want to reconcile this with what we observe in a dynamic analysis. So we run the app and we feed it with input from using Monkey, right, which has been mentioned here before. So Monkey is an app exerciser. So dynamically, we're going to be able to extract parameters, and then we take those parameters, we feed them to Elix, and then we launch these links with via something called a link executor. So a link executor takes Elix-extracted links along with the parameters and launches that in the app. So we tested this on top 1007 Google Play apps, and we're going to see if this was successful, right? If Elix was able to successfully extract the links, and if it couldn't, why, and if it launched some links that led to a crash, why. So these are the results. First of all, static analysis performance. This is a CDF showing how much time it takes per activity. In these 1007 apps, we managed to analyze 38,000 activities. 89% succeeded, and the rest, 11%, didn't succeed because of limitations with static analysis. Either we use FlowDroid, so it has some limitations, and we also had to put some limitations on the symbolic executor. On average, we managed to process an activity in 104 seconds, which for a static analysis is very, very, very acceptable. And we managed to extract 57,000 links. That's 1.7 links per activity. This is the app coverage. This is, if you want, the most important chart from the paper. So the status quo, if you look at these 1007 apps, you see that only 45% of the apps managed to expose more than a link, and only 25% of the apps expose more than 2 links, right? Which is really, really low coverage. When using Elix, we see that we managed to extract more than 2 links for 98% of the apps, and we managed to extract more than 25 links for 50% of the apps, right? So we pulled this curve, so we managed to increase coverage of link-enabled apps and also of link-enabled pages in the app. So to give you an idea as to what we observed with dynamic analysis, so we ran the app with Monkey. As I said, we intercepted the intent parameters, and then we execute the links with those parameters. Because Monkey can't exercise all the activities, it doesn't achieve perfect coverage. It's good, but it's not perfect. We were only able to execute 1,300 links in 100 apps, and then we performed 2 checks. We checked the logs for any impropriety, like say crashes, and we also looked for any state differences between a pure Elix link and something that would be achieved with Monkey, and ideally you shouldn't observe any difference, right? So that means static analysis gives you the precision and reproducibility of dynamic analysis. So we found that for 80% of the app, the success rate was 67%, and for half the apps, success rate was 92%, so on average 84% success rate. These are some examples from well-known apps. These are the number of activities and the activities with links. What you can glean from here is that pretty much all the activities expose a link. These are the tested links, which is a substantial number, right? So 14 for IMDb. This is the number of links where we achieved success, and we were able to successfully exercise pretty much all the links. This is the number that failed, and the reasons why the links failed. So we have what, from 1 to 5 failures for these very, very well-known apps. You can check out the paper, but essentially it was due to limitations with static analysis. If you use dependency injection, for instance, static analysis has some trouble with that, or if you use some funky serialization, or if you use fragments, again, These are all technical obstacles. They can be circumvented with some more effort, but we wanted to be upfront, right? So we managed to successfully link pretty much, or a large majority of these exposed links. Okay? So to conclude, I've presented Elix, an approach that has demonstrated that automatically extracting app links is technically feasible. And we managed to pull, you see the yellow curve is the status quo, very few apps exposing very few links. The blue curve is after Elix, so many more apps expose many more links. We are able to process 89% of the activities in these well-known apps, and we're able to launch these app links successfully in 84% of the cases. There are many possible applications for Elix. For instance, search engines are currently using this to an extent, but they can leverage Elix to essentially give you a much richer interface to how you would land in a certain app. In-house app developers can also use Elix to figure out what links are exposed. Maybe you want those links exposed, maybe no. Well, Elix tells you, nevertheless. And also app stores, because app stores want apps to be successful, right? And if you want to make sure that, first of all, your apps don't inadvertently expose some sorts of hidden links, you can use Elix to figure that out. But you can also use it in a positive sense to expose more links, and then this allows other, let's say, websites to land in a certain page on a certain page in the app, thereby improving user experience. This concludes my talk. I'd be happy to take any questions. Thank you.